putting together what we know from the third corollary to the mean value theorem, along with what we know about critical points, we have the first derivative test for local extreme values. Suppose that C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing C, except possibly at C itself. Moving across this interval from left to right, if the first derivative changes signs from negative to positive at C, then f has a local minimum value at C. Well, when my first derivative is negative, my function is going down from left to right. If I change values at C to positive, my function starts to increase. So it was going down and then it had to turn around and go up. And this is saying that that happens at a critical point, at one of the spots where my first derivative is either not defined or equal to 0. 2. If the first derivative changes from positive to negative at C, then f has a local maximum value at C. Well, when my first derivative is positive, I'm going up from left to right, and where it's negative, I go down from left to right. So I have to turn around. And again, at a critical point, where either my first derivative is equal to 0 or not defined. And then third and finally, if f prime does not change sign at C, then ... And then I'd like to say I put the ... there to give you a chance to think about what the third thing should say, but the truth is I simply ran out of room. But go on and think about what it means if the first derivative does not change signs at a critical point. Well, what it means is at that critical point, maybe I had a horizontal tangent line for a moment, but my function kept going up. Maybe it means I had a horizontal tangent line and my function kept going down. Maybe it meant I had a vertical line, a vertical tangent line, or a vertical tangent line like this. Those are still critical points where my first derivative doesn't exist or is equal to 0, but I either kept going up or kept going down, which means if I don't change sign at a critical point, there simply is not an extreme value. So there's a min if I change from a negative to a positive. There's a max if I change from a positive to a negative. And when I say change, I mean in the first derivative. And if the first derivative doesn't change sign at all, then there's not an extreme value at that critical point, and that's just fine. So let's look at that example we did in the last video and see if we can learn more about the function f of x equals x cubed minus 12x minus 5. In the last video, we took its derivative and wrote down where the first derivative is positive and where the first derivative is negative. And we developed a little sign chart that looked like this. We found the zeros of the first derivative. What we really did was we found the critical points. And we put them on a number line. And then we summarized the signs of the first derivative. And what I know now is that from minus infinity to minus 2, my function's increasing, so it goes up. And then it starts going down from minus 2 to 2, and then it starts going up again. And I know that a polynomial can't have a sharp corner in it like that. In fact, I know the first derivative is 0, but in some sense it goes up, down, and then up again. And so I've changed from a positive to a negative, so there has to be a local maximum value at minus 2. I changed from a minus to a positive, so I went down and then up, so there has to be a local minimum at 2. So f of x has a local maximum at x equals minus 2, and f of x has a local minimum at x equals positive 2. If I wanted to know what those min and max values were, I'd have to plug my x's into the function and actually find the maximum and minimum values. But I'm happy with this for now. One thing I do want to say is that I actually know these are local and not absolute. This is a test for local extreme values, but remember, an absolute extreme value is also a local extreme value. The reason I know that these aren't absolute is that a cubic function's end behavior does this, right? That it's on this way going down forever and on this way going up forever. So even though this is a local max, this goes up forever and there's going to be some y value higher than it. This is a local minimum value, but if I go down far enough on this side, I will end up with a y value that is less than that one.